Hello everyone, welcome to Semiconductor Device Simulation. This is Lecture 6, Time-Dependent Continuity Equation. In previous lectures, we have been focused on solve steady-state drift diffusion equation and Poisson equation. Now I want to introduce you how to solve time-dependent differential equation. I'm going to show you 3 different methods: forward, backward Euler, and the trapezoidal method. And then I will talk about how to solve time-dependent continuity equation along with some code demonstrations. How do we solve a differential equation like this, which is dy over dt equals to some function f? Similar to space, we can also divide time into finite time steps. Now dt becomes h, where h is the step size between ti plus 1 and ti. And dy becomes yi plus 1 minus yi. So now we have get the discretized left-hand side equation. Then how do we deal with the right-hand side equation since we have y here? And here I'm going to introduce you 2 simple approximations, forward Euler and backward Euler. Now if we're using yi to calculate the f, we can get this equation, which is called a forward Euler. And since all our right-hand side does not have yi plus 1 in it, so the equation is explicit. You can simply get yi plus 1. And now if we use yi plus 1 to calculate f, we get another equation where now in the right-hand side we got this yi plus 1 in the f. And this method is called a backward Euler. It can either be implicit or explicit depending on your f. If f is nonlinear, it is an implicit solution, an implicit equation, and we will need to do the iteration to solve it. So how to do that? Similar to any nonlinear equation, let's use Newton's method to solve it. We define a function g, which is equals to yi plus 1 minus yi minus h times f. And we can define g prime, which is dg over dy plus 1. Then now we use Newton's method to calculate the new yi plus 1 using old yi plus 1 and g prime. And then we do this iteratively until they converge. Okay, now I'm going to introduce you a new method to solve that, which is called the trapezoidal method. Since usually for forward Euler, you will overestimate the solution, and for the backward Euler, you will underestimate it. So people start to think about it. Why don't we just take the average between forward and backward Euler so we can get more accurate solution? This is where we come up with this trapezoidal method. So what you do is we simply take the solution for the backward and the forward Euler and we get this new equation. And you can see that in the right hand side, we also have this f as a function of yi plus 1. So if f is nonlinear, we also need to use Newton's method to iteratively solve this equation, where we can also define a g and a g prime to do that. Then now I'm going to show you some simple example to apply these 3 different methods. I would like to solve a differential equation that dy over dt equals to 1 over y. And there is the given initial condition of y is square root of 2. And this equation can be analytically solved, and we get an exact solution, which is y equals to square root of 2t plus 2. Now here I'm showing you some code implementations for these 3 different methods. So you can see that for forward Euler, it is very straightforward. We don't need to do any iterations. However, for both backward and the trapezoidal rule, we need to do the iterations for every time step to get the solutions. Now here I'm showing you the calculated results. For the left-hand side figure, I'm using 11 time points to divide our time. And you can see that the forward Euler solution will overestimate it, but the backward Euler will underestimate the solution. And the trapezoidal rule, which is kind of the average between forward and backward Euler, which is the closest to our analytical solution. And if I'm using more time steps from 11 to 51, now since the time steps become smaller, so the solution becomes more accurate. And now all these three methods can get a solution that is very close to the analytical one. So from this we can observe that the forward Euler, since it is explicit, so we don't need any iterations, so it is the fastest, but also is the least accurate and stable one. And the trapezoidal method is usually the most stable and accurate one among all these three. Now I want to move on to the continuity equation. So I would like to take the electron for example. The continuity equation for n is dn over dt equals to divergence of jn over q plus g minus r. So the right hand side is our f. And I would like to use Slabon variable in this case. So we can rewrite n using a Slabon variable. And then I plug this into our continuity equation and do the trapezoidal approximation. Now we can get this new form of our continuity equation. And fortunately, when we are talking about the drift diffusion equation, we usually consider it as a linear equation. So we can directly solve this equation without using any iterations. Now we got the finite difference form of this continuity equation in both time domain and also in the space. And we can rearrange this equation so that now all the right hand side are calculated from the solution at ti point. And for the left hand side, that is what we want to solve, the phi n at ti plus 1. And then since this equation is linear, we can simply solve that. And now what we need to do is iteratively, self-consistently calculate it along with the Poisson's equation. So what we will do is, from the previous time step, we can obtain the EC, EV, EFN, and EFP. Now we are going to use them to calculate our equations at this time step. So the Poisson equation, which will take into the EFN and EFP at ti plus 1, and then calculate the ECEV at ti plus 1. And the continuity equation will take the EC and EV at ti plus 1, as well as the ECEV, EFN, EFP at ti, to solve for the EFN, EFP at ti plus 1. And we do the Gamow iteration until it converges. And here is my code. I define a new function called tDriftDiff that is for calculating the time-dependent continuity equation, where I have implemented the method I have showed in the previous slides. And I also define a new function called tGamow that is for doing the Gamow iteration between the Poissons and the time-dependent continuity equation. And here I want to demonstrate a case of a p-n junction under light illumination. So what I do is, First, I will calculate the steady-state p-n junction without any light to be my DC solution at t equals to 0. And then after that, I will set up a generation inside our p-n junction, which is used to mimic the light generation of electron and hole pairs. And then I'm going to use my T-gamma to calculate our Poisson and the time-dependent continuity equation iteratively to find out our solution for every time point. Here are some animation of the simulation results. And I have set up some light illumination at the middle of this junction to create electron and hole pairs. And then after that, electron and hole will be generated, and the field inside this p-n junction will drift those carriers out. And then you can see that over the time, our EFN and EFP will be splitted from the middle toward our EC and the EV due to these generated electron and hole pairs. And it is more clear if we look at this carrier density plot. So you can see that there is clearly an increase of N and P due to this light generation, and those generated hole and electrons will be driven out toward the end of this device. And it can be more obvious if I plot just the excess carrier density. And you can see that when the time increases, the electron and hole pairs are keep being generated, so the density goes up. And the electric field will drive out all these carriers so that they will move toward the end of this device. And if I calculate the terminal current of this p-n junction, it is also very clear that when the time keeps increasing, the current goes up because there are more electron and hole pairs keep being generated, and they will be driven out toward the end of this p-n junction and being measured. And eventually this current will saturate it because in this case I'm giving it a constant generation. So in the end, the amount of the current will be generated will become fixed. So the current being detected will also be fixed.